like this is something that is done all the time with, like, sump pumps and hot water tanks, and there's a whole bunch of stuff. So like in my house, our hot water tank has hoses at the top, or rather copper, you know, copper stuff, which actually has an outlet which goes through the center and again picks up everything from a pump which is in the bottom. Or maybe it just adds pressure, but either way. So how much work is this particular thing going to do? Well, it's got to get all of the hot water from the bottom of the tank to the top of the tank and then up to where our plumbing is, which is, a good 3-4 feet above the top of the water tank. So this takes a lot of energy to get the water up this high, which, interestingly enough, also means that this will also, because it just takes energy, it'll actually take thermal energy out of the water when you raise, or when you bring this plumbing higher. It's one of the most bizarre things in the world that I found out, is that, like, if you're actually in the shower and you take the head off of the top and bring it down, it ends up heating up the water that's in the shower head. And if you put it up higher, it's going to drop the temperature. If you don't believe me, try it. Yeah. So anyway, in my house, this is kind of the setup that we have for. We have 2 water heaters, one on either side of the house. I mean, in theory, it could be that it's just exposure to air, but I'm pretty sure. Like, if you just put your hand kind of next to it, both up top and down bottom, then that will control for that variable. And bring it like really far down versus really high up. That's an easy experiment. It could be that I'm just wrong, and that's fine. I'm okay with that. Especially in wintertime. Whoa. Anyway, so for this one, this ends up being a little fun. The measurement that you want to do is the measurement of how far down is this going to, is the water just naturally going to drop? So the water will naturally drop to this level if you just let the pump go slack. And like have an outlet which will completely nullify the pressure. And then if you want to get any more water out than the hose level, you have to push and pump more. Put more pressure into the system and pump it down further. And so that will cause it to end up being down here. And this will cause us to use, or require us to use, work to get below the outlet level. So this will require work which is positive, so it will push, we have to do the work to push the water up to this particular level. If it's up here, we actually get negative work. So for instance, if you wanted to completely empty this tank, and it was, let's say, 5 feet tall, and the water was at 4 feet, and the outlet pipe is 2 feet above the ground. And again, we want to completely empty the tank. Then this is going to require right, so if we let this be 0, come on now. Ooh, there we go. All right, and the water tank itself, come on. It's a radius of, let's go with 2 feet. All right, so then work is going to be equal to the amount of force that's needed to do something times the change in the distance that it's going to take to get from one place to another. Oh man, gonna get myself into a lot of trouble doing this one. Alright, so the force to be able to move any particular layer of water are going to be cylindrical. And so their volume is going to be our pi r squared times the height. The height in this particular case is just going to be a small dx or delta x. Our r is 2. And we get a pi here. So our volume is going to be 4 pi delta x. So again, that is the volume of any particular infinitesimal layer of water that we make throughout this entire water tank. So then the force required to move that water is going to be the volume of that water times its density. This delta x is not the same as that delta x. Smart. We'll just call it distance. All right, so this is going to be 4 pi delta x times technically this is going to be like feet squared. No, cubic feet, right. Okay. And then the density of the water is going to be pounds per cubic foot, which is 62.4 pounds per cubic foot. Yeah, it is listed here, so I didn't just know that off the top of my head. I'm not that focused. Oh, you know what? It would actually be easier if we let this be 0. Right, because that's our target height that we're trying to get to. Do you want to throw one in, or is it just a matter of like, this is becoming overwhelming? Alright, this is going to be times the distance. Yeah. Like I said, if you want to throw one out there and interrupt me, feel free. Oh, is it going to be that easy? Yeah, okay. So I think this is going to have a net 0. Of course it does. Because the 2-foot mark is halfway up the water column. So it's 4 feet tall. And the 0 level is 2 feet up. So we're going to have gravity doing all the work for the first 2 feet, and then the pump doing all the work for the last 2 feet to get all of the water out. Yeah. So this is going to end up being the ith. Yeah. So our x distance is going to be evaluated. So this is going to be the work equals integral of all that stuff, which is going to be a constant. And our distance is just x. So this is going to be 62.4 times 4 is going to be 249.6 times pi times x dx. But this is evaluated from -2 to +2. And again, oh wait, hang on. Well, that is going to be an x squared. Alright, give me one. All right, anyway. So yeah, the work should definitely be negative at the top section. So our result, oh, right, okay. Jeez, man. Clearly not enough coffee. So, no, this is good. It's supposed to be the same value. So we end up with, this is going to be a 249.6 pi times x squared over 2 evaluated from -2 to 2. And when this happens, we get a 249.6 pi times the quantity. This is going to be 2 squared over 2 minus parentheses 2 squared, -2 squared over 2, which now this is going to be 0. So it eliminates the whole thing, and then the work done in this particular case is 0 joules, because all of the work of the water column pushing down is going to be then balanced out by all of the water all of the work done by the pump to press out the rest of the water column. Now we could do something rather interesting of like making it like this. Say that any given slice is going to have to then, where would be the like optimal placement of this? Let's say we wanted to do 0 work. From full to empty. So that could be one example where you'd want to figure out like where exactly are we going to place the hose in order to do 0 work to get this from absolutely full to absolutely empty with no work done. That would be an interesting problem, although I think it might be beyond the scope of this particular problem type. All right, anyway, Matthew. Go right ahead. Okay, lines made of points, even though points have no length. True? Might see where you're going with this. So continuity in terms of calculus, has 3 parts. And for the most part, like, real analysis is the course that you would use to really delve into this stuff. But basically, in terms of calc, so for what's the wording of this? For every point C belonging to open interval A to B. So first main point is that f at C has to exist. Okay, so for every single point that you pick on some open interval, that particular point has to exist in the first place. All right, easy enough. Also, the limit as x approaches C, and this is double-sided, of f of x exists. So for this, we're saying that both sides have to approach the same value. Yeah. Or even just like piecewise. So, I mean, that's why it's called piecewise discontinuous, is when you have a step. So we don't want any of that. And the third one, that was actually very important, is that f at C is equal to the limit as x approaches C of f of x. So f at C has to exist. The limit as we approach from both sides has to exist, and those have to be the same point. So some of the examples that we always throw out to students are like, okay, f of C, if it doesn't exist, like, so if we want to break, then anywhere that there's a hole is going to be f of C doesn't exist, so this doesn't work. Therefore, this is violating rule 1 of continuity. Limit x approaches C of f of x exists would be something like a piecewise function where all the numbers are covered, every point exists between A and B, but the limit does not exist because we have 2 different approaches. So this violates rule 2 of continuity. And then the other one was like, what passes the first 2 but doesn't actually pass the third? It would be something where the limit exists, but the function is actually a completely different point. Yeah, so this violates 1, violates 2, violates 3. So in terms of a line, it has to pass all 3 of these in order to be continuous. So you're saying, like, no matter what point I pick, or no matter what interval I pick, right? No matter what point on that interval I pick, that point exists. The points around it are leading up to it, and also those points are the appropriate limits. So that's going to be the definition for continuity on literally every single point between A and B. In 2 dimensions, this gets interesting, right? Because now you're saying, like, in an area, if I want this rectangle to be continuous, like a continuous region, then I'm saying that I want to pick a particular point. And again, this is infinitely every point in the entire region can be done the same way. So, so this particular point, you know, CD must exist, is going to be, again, rule 1, right? So there exists some delta and epsilon, or I think we just need epsilon. There exists some epsilon such that so we'll call this point C. Capital C. So some point C, C comma D exists. Has to be rule 1. Rule 2, similar to this, is that for some epsilon, all points whose distance, I don't want to do D. Yeah, but I'm for all points, you know what? Let's do this. For all points X, the distance between C and X must be less than epsilon. Epsilon is an arbitrary distance. So there has to be some sort of distance around C, which we can call epsilon, for which all points in that region exist. I'm wording this very incorrectly. Such that exist where? That's slightly better. Yeah, and I don't remember, like, there has to be some sort of, like, there has to be a third condition, but I don't remember anything about it. My analysis book is in my office, so that's halfway across town. I haven't been there in a year and a half. Yep, so some arbitrarily small epsilon must contain some points Like no matter how small it is, it will contain points. And those points will be a distance away from C, which is less than epsilon. Which does mean that the entire like outer edge of this region is open. So just like our just like our points up here, A to B on a one-dimensional line, like these have to be open intervals as well. So here, this is an open region. I was just talking with my daughter about this actually. Yeah, in one dimension, that's all you've got is point, ray, line, and segment. Yep. So you can construct any sort of angles, any sort of closed figures. Well, you can't have open figures technically because the regions need to be finite in size. I guess they don't have to be finite in size. They can go off to infinity, but right. So continuity can go